Welcome to solverfy.
Looking at problem on tension and friction, consider the diagram shown in the board. We want to determine what required maximum force can be applied. That force P there can be applied to the system without causing motion. To solve this problem, we will apply friction principles, equilibrium, as well as belt, pulley, tension relationship. So that if we consider the top diagram, we have a summation of the forces that are there. Okay, summation of the forces. Uh, if we take moment of the forces about E for the top diagram, I'm going to have minus T times 0.4 plus W1 times 0.0.15 to be equal to 0. So that when we solve this, we are going to have our tension there to be 36.8 Newton. Okay. Now we can look for consider summation of forces in the horizontal direction. When we do that, we are going to have the frictional force at B, the frictional force at B, okay, minus T, tension going to the uh, left there to be 0. So when we take our, this one is going to give us FB is equal to T, and we know the tension to be 36. So if the tension is 36 and FB is equal to T, therefore FB is equal to 36.8 Newton as well. Okay, having done that, we can consider equilibrium in the vertical direction, so that we will now have summation of forces in the vertical direction to be equal to 0. Okay, to be equal to 0, so that we will now have minus W, because W will be coming down, W1 plus normal reaction at B to be equal to 0. So if we do that, we can get our normal reaction at B to be equal to W1. And if it is that, therefore NB or N subscript B, normal reaction at B is equal to 98.1 Newton, because the weight subscript 1, W subscript 1 is equal to 98.1 Newton. Now, having done that, we can consider equilibrium for the bottom part of the diagram there, so that summation, okay, so that summation of the forces in the horizontal direction will be equal to 0. Okay, so we have the forces there, F subscript A, sorry, FB, F subscript B to be equal to, sorry, minus S subscript minus F subscript A, which is frictional force at A, plus the tension that is going out to the right there. You can see T subscript 2 star is equal to 0. If you do that and solve this one, you're going to arrive at the value of that force to be equal to FA or F subscript A plus F subscript B. Okay. Now, if we consider equilibrium in the vertical direction, we're going to have the summation of the forces in the vertical direction to be equal to 0, so that the normal reaction at A minus the normal reaction at B minus W2, okay, it's going to be equal to 0. So that when we solve this, we are going to have our NA, normal reaction at A, to be equal to N subscript B plus W subscript 2, W2. So the answer there, since we know NB already and W2, the weight of W2, when we add them together, you're going to have it to be 166.8 Newton. So that is the value of the normal reaction at point A. Okay. Now, having done that, we can look for the frictional force. The frictional force at A. We know that FA is equal to mu, the coefficient of static friction. Since we are talking about that surface A, the coefficient of static friction there, okay, NA, normal reaction at A, that surface, here it is, and the other surface is uh, contacting with. All right, so that when we multiply, we are going to have the values already given there, 0.3 times W. So remember that NA is W, is 106.8. Sorry, uh, NA is W1 plus W2. When you put the value there, W1 plus W2. So when you put the values there, you're going to arrive at your answer to be equal to FA to be equal to 50.04 Newton. Okay. Now, having gotten that, we can look for the tension T2A. So that one is going to give us is FA plus FB. So when we do the addition there, we are going to arrive at E to be 86.84 Newton. Okay. Now, but remember that we've not gotten the tension on the tight side of the belt. So it is T1. Okay, that T1 is the tension on the tight side. T2 is the tension on the slack side. Okay, so the relation is this. This is their relation, and of course, we have mu there. The angle of wrap there is actually just 180 degree. So it's actually 180 degree. So when we solve this one out, we're going to actually have it to be, we can get our T2 from here. When we make T2 the surface of the formula, we're going to have it to be T1 of course. The coefficient of friction at that point where we are considering now is mu is 0.1 for that the belt there, and between the belt there and the pulley there, 0.1 times times pi. Angle of wrap is 180 degree, which is pi. So when you do that, you are going to arrive at 0. Okay, 0.73 T1. Okay, so you cannot solve when you, of course, we know that from the diagram there, you can see that T2 has been stated that it is equal to, or defined that it is equal to T1 prime, T1 star. Okay, T1 star. So the system. Okay, T1 star. So having that in mind, we can now bring out. Jeff, we are going to have 0.73 T1 to be equal to T2 star. Okay, mu. So at that point, we are considering for the other pulley, the friction, the coefficient of friction with the belt there is 0.4, and the angle of wrap there considered is uh, 90 degrees. So 90 degrees is pi over 2 rad. So when you solve that, you're going to arrive at your T2A. Okay, so T2 star rather to be equal to 0.31, 0.3939, okay, T1. So, and of course, we already know our T2A before. That T2A is 86.84 Newton. So we want to plug it in there, we can get our T1. Just plug in the value of. So we're going to have T1 to be equal to 86. Okay, 86 is 6.84 over 0.39. 0.39. So the answer there is going to give you equal to 222, okay, 0.92 Newton. 0.92 Newton. Okay, so this is the. So, and of course, this value is equal to P, because we have already defined it that on the bed that P is equal to T1. Okay, so the force that we are talking about, that force P is equal to 2. So that's the value. Okay, that's the maximum force that is required. That